So, if you remember, last day we actually uh, discussed about okay uh, that gravitational wave, okay, and we discussed about radio telescope, X-ray telescope, and on the first class we discussed about the basics of telescope, why we need a telescope, and what is basically a telescope, etc. And we discussed that there are many kinds of telescopes are there according to what kind of light it sees, something like whether it is a visible light or infrared or radio or X-ray, gamma ray, like that. And then later we have seen how basically an X-ray telescope work, or what is a radio telescope, one or two examples of each of them. That is what we discussed. So that is about the types of light in which the astronomers are actually observing. Then we discussed about something new, relatively new when compared with the other thing, that is the gravitational wave, which only just started to just observed only in 2015, just 10 years back. That's it. So, that is called the gravitational wave. So it is not actually the what is called the it is not the light, actually usual light. It is something else. And so now, then other than this gravitational wave, there are many other things are actually coming from space. And one of the most important thing that is coming from space is something called a tiny particle, tiny low mass particle called a neutrinos. Okay. So these particles are called subatomic particles. So I don't know whether you know about subatomic particles. Anyway, I will give you a brief intro. Something like, if you take a material, something like if you have a pen in your hand or something like a paper in your hand, you can actually make that paper take a paper or take a pen and make it half. Okay, then you will get a piece. Or simply, we can take a smaller thing, something like a sugar cube. Okay, that you're seeing, that's there. So if you make that cube smaller, again smaller, I'm slicing half. I will take one piece and make it half, then take the other one and make it again half. So you can go up to a smaller level, and finally you will reach somewhere called an atom. Okay, so basically when you see materials are made of, we say that element. So water is made of hydrogen and oxygen, and if you split water you get hydrogen and oxygen. So if you look inside hydrogen and oxygen, it is something like an atom. So that basic unit is called an atom. But even you can actually split atoms so that you get many things called electrons, protons, neutrons, many other particles are there. Okay, so similarly there are many other particles are there in the universe. These are not the only particles that we have. There are many tiny particles. Okay, so those are together, sometimes we call it as subatomic particles. So neutrino is a tiny subatomic particle, actually. I'm not going to explain how we discovered it, how we know that it exists and all, but they are electrically neutral, extremely light, but it has a certain mass. As low mass is there, but it is not massless. Okay, it has a tiny mass, very weakly interacting with the matter. So the problem is that it won't interact with others. Okay, for example, light is coming. Okay, you know that the light. Okay, so when you are seeing this class, actually light is coming and it is actually making some interaction with your eye. That is why you can see it. Okay. But in the case of neutrinos, it is not interacting at all. So that is another speciality of neutrinos. Okay. And neutrino has a speciality that nothing can block almost it. Okay. Usually to block particles or radiation, something like that, we can place some lead block. Okay. Lead is a metal. A lead block or a big concrete, then lead, etc. So it will be blocked. But in the case of neutrino, it can actually pass through lead walls, planets, stars, without even any interference. Okay, without interacting, it can actually go through anything, actually. So everything is transparent. Almost everything is transparent for neutrinos. That is why it is called gauss particles. So okay, so an interesting number is that every second, that means even during this class, every second 100 trillion neutrinos actually passing through our body. So even right now 100 trillions of them are actually passing through our body, but we won't feel anything or we can't see them. Okay, so that much light and tiny and less interacting, weakly interacting is neutrinoids. Okay, and there are different types of neutrinos are there. Just leave the names actually. You won't understand it for now because these are all some. Anyway, there are three types of. That's only thing. And what are the sources of it? It's coming from sun, cosmic rays, supernova, nuclear reactors. These are all so I will discuss what is cosmic rays in the coming slide. Okay, so there are from sun, from everywhere in the universe. Actually, neutrinos are coming, and all the sources are not yet known as well. That is also because neutrino science is or neutrino physics is actually relatively new when compared with others. So we don't know much about them. That's also another thing. But anyway, it is coming. So we want to observe them, or we want to see how many that coming. We want to see its properties, etc. So for that, to observe neutrino, we have neutrino observatory. Okay. So what is a neutrino detector on an observatory? Neutrino detector or observatory is designed to study neutrinos. Okay, but it is a weakly interacting particle. Then how can we see them? That means I already told that the trillions of them are actually passing through my body, but I cannot see them. But there are indirect methods, or there are methods for detecting neutrinos. So one method is called scintillation method. Another important one is Cherenkov method, then radiochemical method. These are some of the methods for finding neutrinos. Okay, so I will explain radiochemical detection. So it will be something like some kind of a chemical will be taken inside a large container, and when neutrinos pass through that, some of that, a very less number of those elements will convert to some other new elements. So then we can count how many new particles are there. Based on that, we can have a count of neutrinos. So then there is something called a Cherenkov radiation. So this is what you are seeing here. Okay, this is Cherenkov radiation. Here you can see a glow. This is from a nuclear reactor. So this glow is basically something called a Cherenkov radiation. So by Cherenkov radiation, you can detect. I'm not describing them what it is because it is actually beyond your level, but just understand the methods, or just keep in mind that there are methods to detect them even though they are weakly interacting. Just see the names, that's all. Okay, so that is how it is actually we are detecting. So, and their observatories are so different, so interesting to see them. So one is this called the ice cube neutrino observatory. Okay, so it is something like this. So this is the ice cube neutrino observatory, which is actually located in South Pole, Antarctica. And see the depth. It has some depth and size. You can see it is actually 2.45, 1.45 to 2.45 kilometer below the ice surface. So if you go to Antarctica, just this is the surface. That means it's completely ice, and this observatory or that observation technique and those instruments are not on the surface. This is just its office and control center, what you are seeing in this figure. But actually, those instruments are placed some 1.45 kilometer, 1.5 kilometer to 2.5 kilometer below ice. Okay, it's inside that. So it is something like so tiny tubes actually. And when neutrinos come and pass. So neutrinos are not the only thing. There are many other things are actually coming from space. So we want to isolate them. So there is an advantage of having ice. So after passing many materials, so neutrino will be there, maybe some other electrons, protons, everything is actually coming, but ice will block almost everything. And what remains is neutrino. So neutrino get detected here by producing again a Cherenkov radiation there, a blue flash of light, and by that flash of light, this instrument can actually detect. Okay, so it is something called a 5160 digital optical modules are there. So I will show you the structure. So this is the top of ice. See, this is the top of ice, and using many other strings, actually there are these tubes. This is the detector. Okay, so this is the rock beneath. So this entire part is actually ice, and this each of this rod, okay, or this ice cube detectors, this solid or digital optical module, each of them. So this is what you're seeing at inside. See, it is something like a drilling a hole through that ice and putting some all these instruments, okay, or this long digital optical module, and it will be detecting the neutrinos. Okay, so this is one called the Ice Cube Laboratory or Ice Cube Observatory, which is located in Antarctica. Okay, South Pole Station. Okay. Now, this is another one. This is called the Super Kamiokande. I don't know whether the pronunciation is correct or not. Anyway, this is the another one, Super Kamiokande, which is another observatory. And this is also something like, you can see this beautiful picture. See, this is actually something like a large well. Okay, you can imagine it as a large well. The well is so large, something like its size is something 41-meter tall and 39-meter diameter. So it is, its diameter is 39-meter and its height is 41-meter. Okay, so it's so tall and it's a huge well. So inside that huge well, ultra pure water is filled. Okay, so there is water inside that. Okay, so why again water? So through the water, this neutrino can pass and it will make that glow, that Cherenkov radiation will be made. And this, you can see something looks like gold here. Okay, some bowl kind of thing. They are all situated on the surface. They are not actually gold balls or anything. Okay, they are all around it. Okay, so they are something called photomultiplier tubes. Okay, they are called photomultiplier tubes, which is a kind of an instrument in physics or in science that is actually used to detect this small light. Okay, it's so faint light, normal camera or anything, or if you go and see, it's actually not it may not be easy to see, but to detect them we need some device. So to detect those faint light, that instrument is called the photomultiplier tube. So all this one, each of them looks like a ball. This is actually a photomultiplier tube. Okay, so using this photo multiplier tube, you can actually observe or detect the Cherenkov radiation. So when Cherenkov radiation is there, it might be due to the presence of neutrino. So this is another neutrino observatory. Okay. Now there is one more kind of particles, or one. It is not just a type of particle. There are many kinds of particles. Something called a cosmic ray. Okay, so this is called a cosmic ray because one thing, its origin is cosmic. So it is coming from everywhere. So they are highly energetic particles. So again, it is some kind of particles which consist of proton, some nuclei, some electrons, and they travel through the space. Okay, it's always traveling. So this has another implication, that is when you go to space, the problem is that this kind of cosmic rays actually cause issues for astronauts. Okay, so they should be shielded, and every electronic instrument that is going to space should be shielded from cosmic rays. So having exposure to cosmic rays for a long time is actually not good for health, not just for the health of human being, even the health of instruments as well. So but we luckily have something called atmosphere. So the atmosphere will react with these particles, and it will make some harmless particle as secondary. So it is high energy particle. These high energy particle become low energy by interacting with the atmosphere, and finally we receive a low energy particle on the Earth's surface. So we are actually safe here. But to detect cosmic rays, one thing what we do is that we have something coming. Okay, this is the original thing. You can see these are the original cosmic rays, but it will become a secondary another thing. Okay, it will react with the atmosphere and it becomes some other particles. So these particles can be detected on the surface of Earth, and that is how we can study the cosmic rays actually. Okay, so we are not directly detecting them, but there are direct detectors even in International Space Station, or maybe sometimes in some balloon experiment and all. Actually, there are ways to detect them direct cosmic rays. We are actually detecting usually all the ground-based observatories are detecting the what is called the secondary cosmic rays. Okay, so that is about the secondary particles. Then air shower rays. Again, Cherenkov detectors will be there. Balloon or satellite experiments. Then fluorescent telescopes are there. It is something like fluorescent telescope means it can observe the faint UV light emitted by atmospheric nitrogen. Okay, so during this shower of cosmic ray, the nitrogen in our atmosphere, you know that more than 70% is actually nitrogen, and this nitrogen will emit something called the ultraviolet light. So it can be detected with the help of fluorescent telescope. So that is also there. That is also another method of observing. So these are all some examples of cosmic ray observatory. Pierre Auger Observatory in Argentina, Telescope Array Project in Utah, USA, Ice Cube Neutrino Observatory. So again, we are repeating the ice cube neutrino because it is basically neutrinos are also the part of this cosmic ray observer, the cosmic rays. So that is what. Then Cascade Grande in Germany, now it is decommissioned, and HAWK High Altitude Water Cherenkov Observatory, Mexico, detects gamma rays and cosmic rays using water Cherenkov technique. So these are all the major cosmic ray observatories. Okay, that is another one. Now let us go and discuss about satellites. Okay. So let's discuss what is an orbit is. Okay. So that is the first thing what we how to discuss. Okay. So here you can see this is actually a thought experiment that is actually devised by Newton itself. So imagine that you have a cannonball being fired. Okay. So if with less amount of explosive, if you fire it, it actually goes like this and come back to Earth's surface. It is just imagine you are standing and throwing a ball or maybe some stone or something. It will come back actually. Then if you give some more energy and or with some more force, if you throw it, it will go here. And even if you increase that force more than that, it can actually orbit. So what is actually happening here? So here in the first case, it is falling to Earth. Again, in the second case as well, it is actually falling to Earth. In the third case as well, it is actually trying to fall to the surface of Earth. Okay. Then what will happen? It is actually making a circle. Okay. When the speed is perfectly balanced, it is actually trying to fall, but the curvature of the this or the path of this cannonball and the curvature of Earth being the same. So curvature of Earth and curvature of this stone are the same, so that it is trying to fall on the surface, but unluckily it cannot actually fall. Okay, so it is actually started to move around it. It is always trying to fall to the surface of Earth, but it couldn't. So if you put some more energy, it will make a much more bigger orbit, something like maybe an oval. You can see something like this. And if you give some more energy, it escapes from Earth's gravity. Okay, so it escape. That escape is called, or that speed is called escape velocity, which is 11.2 kilometer per second. So if it is less than that, if you are throwing something less than that, then it will actually keep on orbiting around that. So that is why actually, if you have seen videos of rocket launch, okay, imagine that this is Earth, so big, okay, and if you launch a rocket, you know that the rocket initially goes like this, okay, it will go upward. But if you keep on watching its video, you can see that it is actually not going straight. Eventually, when it reaches somewhere over here, it is actually change its orientation, something like this. Again, it will change like this, okay. Then finally, it makes a orbit that to orbit around. So the rockets are actually not going to the orbit straight away. It is actually making a curve and it is actually orbiting like this. So that is how it is. Okay. So, and the minimum velocity that you need to achieve is something like 7 kilometer per second. Then it can actually orbit around it. If it is less than that, it will come back to Earth actually. So that is how it is moving in that orbit. So this is an interesting thing. This object, every satellite that is actually orbiting around Earth is always falling towards Earth. Okay, so it's a falling thing. It's a falling orbit. Okay. That is how we describe orbit. So every satellite is actually trying to fall to Earth, but the problem is that it is falling in this orbit, so that the curvature of that and the curvature of Earth are same, so it cannot come to the surface of Earth. Okay, so that is why we call it as all the satellites are in free fall. It's called free fall. Okay. Now let's discuss something interesting. So during this free fall, we experience something called a zero gravity. So there is a problem with this naming. So when we hear zero gravity means we think that there is no gravity at all. So zero gravity doesn't mean gravity at that place equal to zero. So this is not the meaning of that. Okay. So we experience, actually more properly, you have to call it as zero gravity, or we should call it as weightlessness. Why? So imagine if you had experience inside a lift. Okay, so imagine that you are inside a lift actually. So this is a lift actually. You are entering this lift, and when you, from the ground floor, assume that you are going to the 11th store or something. Then when it is moving upward, you feel that when it starts to move, you feel that your weight is slightly increasing, or you feel that you are more pressed to the ground. And in the same way, when it is coming from a top floor to the ground floor, something like this, when it is starts to move, you feel that you are not that much pushed to the ground, or something like a slight decrease in your weight you will feel. Okay, so that movement or that is something happens with a slow moving lift. So now imagine that this lift is actually connected to some wire and all. So accidentally this broken. Okay, so this lift it's tied somewhere, and that cable actually broken, and you suddenly fall under Earth's gravity. So when you start to feel, actually for a few seconds, maybe 1 or 2 seconds, you can actually float inside the lift. Okay, why? Because you are falling freely to the Earth. At that time, you won't feel any gravity at all. That is the same thing happening with the satellites. Okay, or even in the, this is from International Space Station. So International Space Station is not that far away. It is just some 500 kilometer away. So 500 kilometer means the moon is even 3,84,000 kilometers away, 3 lakh kilometers away. So at that distance, actually, even the gravity is experienced by the moon. Then something at 500 kilometer will experience Earth's gravity. But since they are, that International Space Station is also a satellite which is actually falling, the people inside that will feel something called zero gravity, or we call it as weightlessness. That is a more proper usage. So we get a feeling of no gravity at all, but still Earth is actually giving a pull to that satellite. Okay, so that is why it can orbit. Okay, so now the question is how high all these things are. Okay, usually, so the limit is actually something like 100 kilometer. Usually, where the space begins. You know that there are many layers: troposphere, stratosphere, mesosphere, and above all, actually, we define a distance that is 100 kilometers, just 100 kilometers. Okay, so this is some 100 kilometers. Okay, at this 100 kilometers, if you go above that, you will be known as a space traveler, or you went to the space. So if you need to be known as an astronaut or a space traveler, then you have to cross this line. There is no such line is drawn really, but this is it. So you have to go upward in that direction. But again, we are not going like this. We will go in a rocket like this, and we will achieve this orbit. Maybe we may orbit, or we will go like this and come back and land somewhere. So that is how it is actually, how the space travel is happening. It may orbit as well. So that is the international boundary, or this is how international definition where the space starts is 100 kilometer above Earth's surface. Okay, now you can see this is the carbon line, and the space shuttle is something around 320, or something between 300 and 400 and 700. Somewhere the International Space Station is here, and many satellites are actually at this height. Other satellites, okay, you can see. So this is it, and aurora is actually happening at that height of International Space Station, and these are the height at which the meteor is happening. And stratosphere, the lower part of the stratosphere, the commercial airplanes are actually traveling. So from this is something around some 11 to 12, 13 kilometers. So that is why even if you fly or you have experience with flight, you are not a space traveler. So you have to travel even some some 80 to 85 kilometer more, then only you can reach the carbon line. And one more interesting thing is that as you go up in this direction, the atmosphere becomes thinner and thinner, and finally there won't be any atmosphere at all. So the problem is that in that thin atmosphere, you can actually fly a usual aircraft. because it is flying. Okay, so a bird cannot fly, an aircraft cannot fly. The only thing that works there is a rocket actually. Okay, and there is another interesting thing. If you're NASA, according to NASA, there is no need to go to 100 kilometer. Even if you go to 80 kilometer, then you reach the space according to NASA. Okay, so that is the definition for NASA. But however, internationally, 100 kilometer is accepted as space. Okay. Now let's see the orbits actually. So these are something about the orbits in which the orbit means when something is there. So if Earth is here or any planet, or it can be a sun. Okay. So now because of gravity, when something is projected and near to it, and the gravity can actually pull it towards. So imagine that I am throwing a stone or it's a comet. So it can come like this and it will try to either orbit, or if it is high velocity enough, it can actually go back. So it get a special shape. Okay. So sometimes if the velocity is proper, then it can actually orbit. For the case of Earth, Earth's speed is so proper so that it can actually orbit in an elliptical shape. So based on its speed, actually, speed of that object that is trying to orbit, the shape of the orbit will be different. So that is in general the shapes of orbit. But according to Kepler, there are three laws of orbit. That is, the one thing is the Kepler's first law, that is each planet orbit about the sun in an ellipse. So it may be obvious for you because you already know that every planet is actually orbiting around the sun, not in a circular shape. We call that shape as ellipse. Okay, but imagine that at that time, at his time, at Kepler's time, it is not an obvious thing. Okay, not everybody's knowledge it is. Okay, but for you this is obvious, but at that time it wasn't obvious. So that is and that particular shape is called ellipse. So to draw an ellipse, actually you can place two pins and a thread. Then you can actually keep moving that thread, something like this. You will get a shape like this. And those points where you put the pin, and those are called the focuses. It has two foci. Okay, one is this focus and this focus, together we call it as foci. Okay, so sun will be here. Okay, and the planet will be orbiting like this. Okay, anyway, we doesn't have two sun to have in two foci, but this is how it works. Okay, and there is another interesting law that is called the Kepler's second law. So I'm not going to explain what it is in its proper way. Okay, proper way is a bit different, but I will explain what happens. So imagine that this is sun and this is Earth, and Earth is moving in an elliptical orbit. So you know that when it is reaches here, so since it is an elliptical orbit, at this point it is actually the farthest point. And here, when Earth comes here, this is the nearest point. Okay, so sometime it is the farthest, sometime it is the nearest. Okay, so if you take the same case of Earth and the Moon, okay, sorry, I will draw another one. Earth and Moon, okay, something like this. So here also we have that farthest point and the nearest point. You may feel that this is the nearest, but this is the problem with my drawing. Okay, so this is the nearest point. So this farthest point is called apo. Okay, since Earth is at the center, we call it as apogee, and this point is called perigee. Okay, and here also, in the case of if sun is at the center, we call it as up. Again, here it is peri, and since sun is at the center, we call it as helion, because the sun is known as Helios. Okay, so this is perihelion and aphelion. So what is about the Kepler's second law? So according to Kepler's second law, when the planet is farther from the sun, okay, or that orbiting object is farther from the object at the center, it will go slowly, and when it comes near, it go faster. So the movement is something like it will go slowly. Here, when it comes near this, it becomes slow and slowly comes, and here when it comes here, it becomes faster. Again, it will go slowly. Then when it comes here, it go faster. So this is the way it is actually orbiting. That is the idea of the second law. Okay. And the third law is something like, I will simply explain to you. Don't worry about these values or this equation. Okay, this is anyway. So according to Kepler's law, as you go, so assume that this is a This is a planet. Okay, this is Earth. Okay, so I have an orbit here. I have another orbit here. I have another orbit here. Okay, so in this one satellite is orbit here, another satellite is orbit. This is another satellite's orbit. Okay, so as you go higher and higher, that means as the orbit is distant or the distance to the orbit increases, as it increases, the orbital speed become orbital in the sense that the period in which it completes a revolution will increase. So that means maybe when a satellite is here, it will complete one circle. Okay, maybe in a day it will complete some 16 orbits. For example, that International Space Station is actually orbiting here, and it is actually making some 16 orbit every day. Okay, so that is it. Okay, so when something is here, okay, it's a bit more farther, it may make some 8 revolutions or 8 orbits around Earth every day. So it takes a long time to complete one. So I will demonstrate that by the drawing. Here it may be moving like this, but when it comes near to the Earth's surface, it will be like this, so fast. So when you go, this will be slow. And if you even go farther, then it becomes something so slow. Okay, if you go even farther, it will be a bit more slow. Something like it will take a long time to complete one orbit. So that is the idea of the Kepler's third law. So as the orbit become bigger and bigger, its orbital period, that means the time taken for it to complete a one complete revolution, become more. Okay, it will increase. So that is the idea of the Kepler's third law. So this has some implications, especially the third law is important when you discuss about something called the orbits. Okay, that we will discuss soon. Now just leave this. This is about the Newton's law and all. Just leave it. It's not for you. So now let's what is called an artificial satellites. Okay. So we have a natural satellite, that is moon. Other than that, we can actually send satellites to space. They are actually man-made object that has been placed into orbit by means of rocket. So anyway, we cannot throw anything, even though in the first case or in the first slide, I have shown something like you can actually throw thing, and that is just an experiment. It's a thought experiment. We cannot really do this with something like we cannot throw something so that it can orbit, but we need something called a rocket to place. A powerful rocket is needed to make things orbit around Earth. Okay, so anything that is placed in the orbit, that is actually made something like this rotation. Okay, so that is. So these spacecraft are equipped with the sensitive instruments and cameras for studying Earth and other planets. So the purpose is depends. Okay, we will discuss about the general purpose, why we are actually sending them. Anyway, we know that if there is a camera, it can actually observe the surface of Earth, for example, how the clouds moves, or whether there is a hurricane or something is there, or maybe the temperature, how it varies. Many things can be measured from space. So the advantage of measuring it from space, so it is so easy to see a vast area. It is something like, just imagine a drone, even a small drone that is on some height, it can even see a vast area. That is one advantage. Okay? So yeah, its expansive field of view and improved spatial resolution can collect information much more quickly than ground-based sensors. And just imagine that I am standing here, somewhere here, and I want to see what is happening here. Okay, either I have to go there by means of some flight, maybe by then I have to travel. Maybe there won't be any airport, maybe there won't be any train. Then I have to manually travel there and measure the things. But instead of that, if I have a satellite, I will tell my satellite to take a photo of that place, or when comes it's above that, just take a photo or send me the information what is happening. So that is how it is being done. Even it is actually used for even farming. So a large area is there. If you want to find whether it is okay to harvest or some issue with the crop, it can be analyzed with the satellites easily, other than going to each of them. Okay, so that is the orbit is, and if you know, this is the replica of the first satellite, that is called the Sputnik 1. Okay, now types of artificial satellites. Okay, so the artificial satellites can be categorized based on what type it is. Mainly in many classes we can actually classify them. One is based on their use. Okay, what is the purpose? Okay, so what is the purpose of the satellite? So it can be either for maybe scientific observatories are there, like the Hubble Space Telescope is there, or International Space Station is there. They are actually for scientific purposes, and there are communication satellites for having the communication. Maybe sometimes for internet or satellite communication, we need or we need orbiting satellites, and for weather prediction we need satellites, weather satellites, and there are many other purposes. So based on then navigation satellites like the GPS or GLONASS is there. So there are many type of satellites that is based on the purpose we can classify them, that we will do, but based on orbit also we can actually classify them. Okay, so there are many different types of orbits are there. Anyway, these 5 of them are the main orbits. Okay, when you think these are the main 5 main orbits around Earth. Okay, we are not talking about orbit around sun or orbit around some other thing. We are actually, all those are actually, so for example, you can see that we went to moon, actually Mars actually. So the sun is here, and the Earth is orbiting here. Just outside that, the Mars is here. So we will go to from Earth we will go to Mars, actually something like a special path. That is also a orbit. Okay, so that orbit has a special name, something else. Okay, so yesterday we have seen that JWST is actually orbiting not around Earth, not around Sun. It is actually orbiting around a point called L2. Okay, so that is also another orbit called L2 orbit. Okay, so there are many kinds of orbit. We are only keeping our attention for Earth-based orbits. Okay, so in the first case, one is called the low Earth orbit. The second one, medium Earth orbit. The third one, geostationary orbit. Then the third one, sun synchronous orbit. Then the last one. So these are all the main orbits. Okay, first 4 of them. Then the last one is something called a geostationary transfer orbit, or GTO. Okay, so that is not a real, that is a real orbit, but usually satellites are not orbiting in that geostationary transfer orbit. The satellites will be there for a temporary time. Okay, to go from a low Earth orbit to the high geostationary orbit. So it is a transfer orbit. So it is an in-between path between 2 orbits. Okay, so we will discuss each of them one by one. Okay, so yeah, this is a video of the satellites that are orbiting around Earth. So, but don't think that it is completely just a second. Okay, so this is an image of many satellites. It's a simulation of that. Okay, it's not the real photo. Anyway, we may feel that when you go look outside, you cannot see anything. It's complete of satellite, but this is not the real case. The sense that if you draw this into the real picture, there is enough space in between the satellites actually. So it is not that clumsy like this. Okay, but when you show each satellites like a this big, then you feel that everything is there. Okay, and if you notice here, you can find some interesting thing. You can see a lot of satellites are near the Earth. Okay, so these are something like this. And when you observe that, they are the fastest moving. See, they are moving so fast. And when you come to here, you can see a special path here, something like a perfect circle. You can see it is slower. Okay, this is what I mentioned in the Kepler's third law. That is, when the orbit is near to the Earth, that objects will be moving so fast. Here you can see they are actually moving slower and slower. So this is what is happening there. So this is an interesting thing that you can notice even. And one more thing I will explain to you here itself. See this red circle, okay? This circle of satellites, something going in this path. If you look at it, it is actually orbiting at the same speed as that of the Earth is orbiting. See the speed of Earth orbiting and see the speed of this red circle. They are actually the same. Okay, so it has a speciality. That is why it is moving in such a way, and it is a. And you can also see one more thing. It is assumed that the Earth's equator comes something like this. Okay, and it is actually exactly above the Earth's orbit. So this thick line of red, these orbits are actually an orbiting satellite which is actually moving exactly at the speed which uh, Earth rotates, and which is exactly above the Earth's equator. It has a special name as well. We will discuss it. Okay. Now let's go. First one, the low Earth orbit, or we call it as LEO. Okay. These are satellites which are orbiting or moving at a height of 160 to 1500 kilometer above. So that region 160 to 1500 kilometer above, then it is called a low Earth satellite. Okay. And low Earth orbit is very common because it is easy to access that orbit. So even with a smaller rocket, actually we can put satellites in that orbit. That is why that number of orbits are there. And since it is close to Earth, it can actually take very good pictures of Earth and all, and it will almost complete one orbit. That means it will make one circle within some 90 to 120 minutes, and approximately it will orbit the Earth 16 times a day. That is why we say that International Space Station is actually covering some 16 days, 16 times every day. It is actually making circles. That is why you might have read that something like the people at International Space Station, they see 16 sunset and 16 sunrises. Okay, so this is an example of those kind of satellites. Okay, now let's go to medium Earth orbit satellites. That is called the MEO, or medium Earth. All right, it is an in between. Okay, I will show. So the height is from Earth, it is something like 5,000 to 2,000 kilometer above. Okay, so those are called the medium Earth orbit. And usually the navigation satellites like GPS, especially the GPS satellites, is actually orbiting in medium Earth orbits. So the advantage is that, so if you place GPS close to the Earth's surface, the problem is that to cover the entire Earth, to see the entire Earth by this satellite, you have to place a number of satellites. Okay, number of satellites are needed. Okay, here, a lot of them should be needed. But since it is at a certain height, actually not that much number is needed. With some 4 to 5 satellites, or maybe some 10 to 12 satellites, actually it can completely cover it. So that is the global positioning system. Another one is GLONASS. This is also a navigation satellite system. So this is also orbiting at that, and it takes some 2 hours to 12 hours for one complete rotation, or one complete orbit, or we can say that at least every day there will be some 10 to 2 to 10 orbits it will complete. Okay, so it is not that fast as that of the low Earth orbit. Now another most important orbit is the geostationary orbit. Okay, we are calling it as geostationary. So here you can see a word that is called a stationary. Usually stationary means it is not moving. Okay, so that is the word meaning of stationary. Then what is the meaning of that, or why that word is being used? Is the satellite is not moving? No, it is not the case. Actually, here you can see this is the equator, and okay, and the satellite is at a certain distance. That distance is so important, which is called the 35,786 kilometer. It is not a range. So in medium Earth orbit, we say that it may be between some 5,000 to 20,000. And in low Earth orbit, we say that it is 160 to 1,500 kilometers. But in the case of a geostationary orbit, that satellite should be positioned exactly at a height of 35,786 kilometers. Okay, now what is the speciality of this height? Okay, at this height, the time taken for that satellite to complete one orbit is 23 hours 56 minutes and 4 seconds. And what is that? It is the rotational period of Earth. So the orbital period, what do you mean by orbital period? The time taken by the satellite to complete one circle. Okay, so that is called the orbital period. So time taken by the satellite to complete one circle, or the orbital period, is equal to the time taken for Earth to complete one rotation. Okay, so Earth's one rotation will take 23 hours 56 minutes and 4 seconds, and the satellite will also move at the same speed. So that is the speciality of this height. And there is one more thing. Now imagine that it is exactly above the equator. when it is exactly above the equator, you see, it will move along with the equator. So the advantage is that, suppose this is Africa and I can place a satellite at this height exactly above Africa, just above the equator. So the advantage is that whenever it is moving, okay, whenever the earth is rotating, the satellite will also move along with that. So this satellite will appear to be stationary with respect to Africa. So just imagine that you are standing at this point in Africa. So it can be anywhere, no problem, in equator. So I'm standing here and looking at that satellite. Anyway, we cannot see that satellite. It's so far away. But anyway, just assume that you are seeing that satellite from there. So you can keep on seeing, because you are also rotating along with the satellite. So it will keep on seeing. That is why it is called a stationary satellite, but it is actually not stationary. It is actually moving at the same speed as that of the Earth's rotation. So it appears to be stationary. So that is why it is called the geostationary orbit. Okay. Now, main advantage of that is it is very good for communication satellites. Okay, something like GSAT, INSAT, and United States GOES series, Meteosat. There are many satellites are actually in this place, and main advantage is that, suppose that I want to send a signal, some TV signal from my suppose that, imagine that I have a TV channel and I want to send its signal to the satellites, and this satellite will send back that signal to a wider area, so that every part of the that area, maybe an entire country, may watch that TV program. Okay, they can tune into that channel. So the problem is that if the satellite is something like another, so when I started to see, so imagine that it is not a geostationary orbit, something in between. So I send a signal, the beginning of the movie, and you receive it back from the satellite, and you are started to seeing the movie. But what will happen if it is in a medium Earth orbit? It will go in some other direction, or it will go faster than the Earth's rotation. So it will go away. I cannot see the remaining of the movie. Then when it comes back to somewhere here, again I can watch some other part of the movie. So the communication will be disrupting. Okay, I cannot get a continuous transmission. So if you need a continuous transmission, you have to place it at a height of 35,786 kilometer. That is not the only thing needed, and you have to place it exactly above the Earth's orbit, Earth's equator. Okay, so that orbit is called the geostationary orbit, or simply GEO. And SYNCOM 2 is the first geosynchronous satellite. Okay, so there is one more thing called a geosynchronous that I haven't explained. So what is geostationary? Geostationary, so already we explained, has two conditions. What are the two conditions? The first condition is its height, where it is 35,786 kilometer height. Okay, that is the height of the satellite, height at which it is orbiting. Second thing, where it is located, above equator. Okay, it's not just above, it is exactly above equator. Now there is another satellite that is called a geosynchronous. Okay, synchronous. You can get the proper spelling here. You cannot. Okay, that is called the geosynchronous. Geosynchronous has only one condition. What is that condition? That is, it has to be at a height of 35,786 kilometer. Okay, 35,786 kilometer. That is the only case. Okay, so geostationary means it has to satisfy two conditions. Okay, and geosynchronous. So we can say that all geosynchronous, all geostationary satellites are actually geosynchronous as well, but all geosynchronous satellites need not to be geostationary. Okay, because it need not to be at above Earth. So something like at the same height, if it is orbiting like this, okay, then we can call it as a geosynchronous. Okay, so that is geosynchronous orbit. Now there is one more orbit that is interesting. It is actually moving in a certain way. That is why that name. Anyway, it is actually a medium Earth orbit. Okay, so this orbit is something like it is in between. It is actually low Earth orbit. Okay, so Sun synchronous orbit is there. SSO. SSO is actually a class of low Earth orbit, but it has a speciality. So it is going in a height of 600 to 800 kilometer above Earth, and the orbital inclination and altitude of SSO are calibrated so that they always cross any given location at precisely the same local solar time. So just imagine that you are living at a place, something like maybe in Paris. You are okay. So you are in Paris, and the satellite will come at above your place. Today you are seeing that anyway. You cannot see that satellite, but sun synchronous and low Earth orbit you can see at the evening, just after sunset and just before sunrise. Actually, you can see it as a tiny star moving through the sky. Anyway, just leave it. So assume that you are at Paris and you can see a satellite. If it is a sun synchronous satellite, at around 10:30 in the morning, you saw that satellite just above Paris. If it is a sun synchronous satellite, tomorrow, okay, so today you have seen, so tomorrow also you will see that same satellite at 10. Okay, the next day, the day after tomorrow as well, you will see the same satellite at the same time. So that is the speciality of sun synchronous orbit. Okay, it is something like the sun. Okay, it comes to the place at the same time. So that is called the SSO, or sun synchronous orbit. And this is an intermediate orbit that I mentioned called the geostationary transfer orbit, or GTO. Okay, so GTO means something like, so usually the satellites are not sent. If you want to go to the geostationary orbit, it is so far away. You know that it is 35,786 kilometer away, 35,786 away. And you know that the low Earth orbit is actually somewhere between 152 or 160 to 1,500 kilometer. It's so low. Okay, so this is just thousands of kilometers. It is 10,000s of kilometers, 30,000s of kilometers. Okay, so instead of going directly to this transfer orbit, usually the satellites are actually put into a smaller orbit like this, low Earth orbit. Then when it reaches somewhere here, that means when it is closer to Earth, again its rocket is burned. Okay? The satellite rocket is burned, and it can actually transfer from a low Earth orbit to a higher orbit. So that is that in between orbit that is here drawn in the blue line, that is called the transfer orbit. So it is actually transferring a satellite in low Earth orbit to geostationary orbit. So that is called the what is called the geostationary transfer orbit, or GTO. Okay, so here this yellow line and this red line is being connected with the blue line. So yellow line is the low Earth orbit, and the red line is the GTO, or sorry, not GTO, geostationary orbit. Now I want to make my satellite go from this yellow to the red. Okay, so there is a connecting orbit. That connecting orbit or transferring orbit is called the geostationary transfer orbit, or GTO. Okay, so this is the both of them, the geostationary and geosynchronous. Geostationary means it is at a geostationary and geosynchronous both are at the height of 35,786 kilometer, but geostationary will be exactly above, this is the equator. Okay, it's exactly, the red one is exactly above the equator, but geosynchronous can be at any direction. Okay, so this slanting, or this is called the inclination. So it is a different inclination. So I can also have an orbit like this, which is with another inclination. Okay. So these are all geosynchronous. Okay, now this is a overview of different satellites. Okay, you can see that the outer one, this is called the, this line is called the geostationary, and here you can see the near the Earth, you can see International Space Station is marked here. This is the lower, and this is the medium Earth. Okay, so that is about the different satellites. So you can see Galileo, GPS, GLONASS. These are all navigation satellites. These are all actually orbiting at a height of medium Earth. And here you can see geostationary. So that's it. So geostationary is this inner line, and there is an outer line called the graveyard orbit. Okay, just 300 kilometers above the geostationary, there is something called the graveyard orbit. It is something like the cemetery for satellites, or it's a graveyard of satellites, because you know that the geostationary orbit is actually only a single line, a single circle. So once the satellite completes its lifetime, so being in the same orbit actually is not that good, because it will become a space debris, and it will be staying in the same valuable geostationary orbit. So they will rise that orbit to a certain height so that it will orbit there. It won't interfere with the proper geostationary orbit. Okay, so that is called the graveyard orbit. Okay, so when the satellite completes its lifetime, it will be moved to this graveyard orbit, especially for geostationary, not for any low Earth orbit. Low Earth orbit will stay there, but only geostationary orbits, satellites will be moved to the graveyard orbit. Now, this is something so simple for you, I think, but anyway, I will go through them because the classification of satellites by their function. Okay, so there are many classifications are there. The most prominent four of them are communication, Earth observation, and navigation, and astronomical. Okay, so these are four most common four types. Okay, I am saying that it is most common four types of satellites based on their applications. So the communication satellites. So communication satellites, it is something like this is Earth. Okay. So imagine that this is Earth. Okay. I cannot actually send, since the Earth's curvature is there, or imagine that this is two sides of Earth. I cannot actually directly send signals from here because it is through the ground. There will be building, and the Earth's curvature itself is a problem. So now I can send this to here, and it will send back to here. The same thing can happen vice versa. Okay. So every communication satellite is equipped with something called a transponder. Okay, so transponder means it consists of something called a receiver. So it has to receive the signal and transmit the signal. So an instrument which is capable of receiving the signal and transmitting the signal, that is called, okay, one instrument that having both capability is called a transport. So it is usually used for media transmissions such as radio, TV, satellite TV is there, satellite telephone is there, and even internet can be accessed using that. So these are all called the purpose called communication satellites. Okay. Now the next one is Earth observation satellites, or EOS. Okay. So EOS is basically used to study many things, actually. Many things in the sense it can be used to study rain. It can be used to study what is happening on the Earth's surface, like clouds, or maybe what is happening, is there any hurricane or maybe some cyclones or anything. So to study them, and also maybe for observing what is happening, deforestation, or if you want to observe some crop is there, and some farming and some crop is there, what is happening to that crop. Okay, so it is basically for it's, you can imagine it as a drone, but that drone is actually a satellite which can actually observe whatever happening on the surface of Earth. Okay, so that is generally called Earth observation satellites. Okay, they are observing the surface of Earth, and also military purpose as well, it's being used. And the best example, you can see those satellites image if you go to Google Earth, or even in the Google map. If you turn on the satellite view, you can see those images of the surface of Earth actually. Okay, so there are weather satellites will be there, remote sensing satellites will be there for mapping purposes, and there are many number of purposes are there, but they are generally called Earth observation satellites. Okay. The next one is actually the navigation satellites. Okay, so usually these navigation satellites are all in the medium Earth orbit. Okay, so navigation satellite system constellation. So why it is called a constellation? Yeah, it is something like a star constellation. In the same way, it is a group of. So for example, in the case of GLONASS, or maybe in the case of GPS, it is not a single satellite. It's a set of satellites for a common purpose, that is to work the GPS, to work the global navigation system, that is a GLONASS or something like that. If you need a set, you will send a set of satellites, and those are together called a constellation of satellites, and they are actually orbiting around so that we get the precise location. Okay, by accessing the satellite. That is why it is said that if you want to give your location to your friend that is coming to your home, you have to actually send the location by, not by sitting inside your home. Okay, when you are sitting inside your home, your location need not be that accurate because there is no visibility of satellites. But if you go outside, okay, if you can see the sky in the sense that clouds are not a problem anyway. If you can see the sky, then you your phone's sensor will see these satellites, or the satellite signals can be this GPS satellite signals can be received by your phone, and it can determine its position precisely and accurately. Okay, so that is how it is getting the position, and we can send them. Okay, so that is about the navigation satellite system. So it is actually, you can see this in this picture. Yeah, here Galileo, GPS, GLONASS, these are all medium Earth orbit, and these are all navigation satellites. Okay. Okay. Also, I will show you an interesting thing. So this is the low Earth orbit satellite, and as you go higher and higher, you can see at what height it is. Okay, some 10,000, 20,000, 30,000. This is the height is increasing as you go outward. Okay, and as you go outward, you can also see that the speed of the satellite. So it is 25,000 when it is near, then 20,000, 15,000, and when it reaches the geostationary orbit, it is only traveling at a speed of 11,000 kilometer per hour. So you may feel that 11,000 kilometer per hour is small when compared with this, but actually it's a huge speed. Okay, so then you can also see here this 5 hour, 10 hour, 15 hour, 20 hour, then here becomes almost 24 hours. What is this? This is the speed, or it is a time taken for it to complete one orbit. Okay, so that time is also increased as you go outward. Okay. So navigation satellites, then astronomical or scientific research satellites, that already we know that JWST or Hubble Space Telescope, and also our International Space Station. These are all astronomical or scientific research. So astronomical means, you know, that these are all observatory that we already discussed yesterday. Many of the examples, and scientific research, especially even though that International Space Station is orbiting around us, it is not for fun actually. So we can take people to there and take them back. It is not for money or anything. It is actually those people are going there and actually doing scientific experiments that has to be done at that condition and all. So it is basically some scientific research satellite.